Hello friends out there, this is Sricharan and welcome to our YouTube channel Petroleum MUTINY. Our main objective is to upload videos regarding petroleum engineering subjects, some important topics relating to subject. We'll be doing it 1 to 2 videos per week. So I hope you would encourage us. Thank you.
In this video, we are going to discuss about the gas material balance. The gas material balance consists of two parts. A is volumetric depletion reservoirs. And the second is water dry reservoirs. In this lecture, we will be focusing on the volumetric depletion reservoirs. Basically, the volumetric depletion reservoirs are those in which, due to the production, there is a decline in the pressure, but we don't consider the effect of the water aquifer affecting the production. So, coming to volumetric depletion reservoirs, the material balance is a simple equation in which we consider the produced gas is equal to gas initially in place minus the unproduced gas. This equation has to be evaluated at the standard conditions. Now, for evaluating this equation, we take some constants like Gp, which is the produced gas, at standard conditions. GIIP is denoted by G. It is the gas initially in place, standard volume. Now, G is calculated using this equation, which is V5 into 1 minus SWC into EI. Here V is the bulk volume, phi is the porosity of the reservoir, SWC is the current water saturation, and E is the expansion factor. EI is calculated at initial reservoir pressures and temperature. Before going further, let me first explain about EI. EI is the initial expansion factor. It can be defined as the ratio of volume of the gas at standard conditions to the volume of the gas at reservoir conditions. So it is VSC by V at T, comma T. Now the unproduced gas will be unproduced gas is a gas which we still did not produce at the surface. So if we consider the volume of the gas in the reservoir as hydrocarbon pore volume at that conditions, now these volume when produced at the surface will be equal to hydrocarbon pore volume into the expansion factor at that pressure and temperature. So hydrocarbon pore volume, as we know, is G by EI. The unproduced gas at the reduced pressure temperature in the reservoir and standard conditions will be G by EI into E. Now substituting these results in the material balance equation yield us Gp is equal to G minus G by EI into E, which comes out to be Gp by G is equal to 1 minus E by EI. This is the material balance equation for volumetric depletion reservoirs, in which we did not consider the effect of the aquifer present within the reservoir. Here Gp by G gives us the recovery factor. Now if E is calculated abandonment pressure and temperature, Gp by G will give us the ultimate recovery. Now E can be mathematically, it is given as E is equal to 35.37 P by ZT. So now I is 35.37 Pi ZT, which since the depletion is isothermal, the temperature won't change. So now if we take the ratio of E by Ei, we get P by ZT by P by ZT, which is P by Z by P by Z initial. Now here if we substitute the value of E by Ei in this equation, we get dP by G is equal to 1 minus P by Z by P by Z initial. Now solving for P by Z from this equation, we get P by Z is equal to P by Z initial into 1 minus Gp by G. So from this relation, we can see that P by Z is linearly related to Gp by G. So if we draw a graph for P by Z versus Gp by G, we get this straight line. So if we know the abandonment pressure, now we can know the ultimate recovery. If this is the P by Z value at abandonment conditions, this will give us the ultimate recovery. Now, since we did not consider the effect of aquifer on the reservoir, if we consider the effect of the reservoir, then the hydrocarbon pore volume will get affected due to the chlorine water expansion and increase in the grain pressure because the fluid is being removed from the pores. So the change in hydrocarbon pore volume can be given as minus dBW plus dBW. Here the minus sign is evident because due to the increase in the porate water expansion, there is reduction in the hydrocarbon pore volume. So now coming to the isothermal compressibility of the pores, which is given by Cf is equal to minus 1 by Bf dBf by dGp. Here Gp is the grain pressure, but we know that overburden pressure is the sum of fluid pressure and the grain pressure. At a particular depth, overburden pressure remains constant. So, with respect to depth, the change in fluid pressure is the minus of grain pressure. Which results in Cf is equal to minus 1 by Bf dBf by d of minus Fp, which implies Cf is 1 by Bf dBf by dP. Here P is the fluid pressure. So dBf comes out to be Cf dBf dP. Similarly, dBW can be written as CW dW dP minus. Here CW is the compressibility of water, dW is the volume of the aquifer, dP is the fluid pressure. Now, for the aquifer, we have to consider the size. Either the volume of the aquifer should be large or pressure drop needs to be huge, the fluid pressure needs to be great, since the compressibility of water is small. So now substituting the value of dBW and dBf in this equation, it comes out to be CW dW dP plus CF dF dP. So the reduction in hydrocarbon pore volume can be given as minus of CW dW plus CA dF into dP. This is the change in hydrocarbon pore volume and this is the reduction in hydrocarbon pore volume. Since we have taken the reduction in hydrocarbon pore volume, this comes out to be minus of CW dW plus CF dF into dP. Here the pore volume is V into phi. The phi is the porosity of the reservoir. V is the bulk volume. Since we know that the gas initially in place is equal to V phi into 1 minus SWC into EI. So from this V phi or pore volume can be given as G by EI into 1 minus SWC. So the pore volume comes out to be G by A into 1 minus SWC. Now the VW can be calculated similarly. Here pore volume into the saturation of water in the reservoir drop, which is nothing but apparent water saturation HWC. So VW is equal to V5 into SWC. From the above equation we get V5 as G by A into 1 minus SWC into SWC. So this is the value of VW. VW is equal to G by AI into SW by 1 minus SWC. So now substituting these results in this equation. Reduction in hydrocarbon pore volume is equal to minus of CW VW plus CF VW into E. Substituting these results in this equation we get minus of CW. VW is G into SWC by A into 1 minus SWC. Plus CF into EN is the pore volume, which is nothing but G by A into 1 minus SWC into dP. I have rewritten this equation for changing reduction in hydrocarbon pore volume, which is minus CW into G by SWC by A into 1 minus SWC plus CF into G by A into 1 minus SWC into dP. Now if we take G by A into 1 minus SWC common, we get SWC plus CF into dP. Now in this equation, the mediated balance, reduced gas is equal to initial gas intakes minus unreduced gas. So same substituting change in hydrocarbon pore volume in the mediated balance equation, we get reduced gas is equal to G minus CP into E. Now in this hydrocarbon pore volume, we need to include the reduction in hydrocarbon pore volume, which is the effect of expansion of porous water and the reduction in the pore volume. So reduced gas Gp is equal to initial gas G minus HCP plus DHCP into E. That implies Gp is equal to G minus hydrocarbon pore volume is nothing but G by EI. G by EI plus reduction in hydrocarbon pore volume, which is this minus G by EI into 1 minus SWC into CW SWC plus CF into dP into E. On solving this equation, we get Gp by G is equal to 1 minus CW SWC plus CF This is the modified material balance equation for gas reservoirs. Now, after inclusion of the term of reduction of current over volume, they get this additional term. So, the change that is induced in the material balance equation because of the inclusion of this term is approximately 1 to 2%. So, in general material balance calculations, this term is neglected, and the original mass balance equation Gp by G is equal to 1 minus E by I is considered. So in the coming lecture, we will talk about the water drive reservoirs. Thank you.
Thank you for watching the video, and if you have any doubts, please let us know in the comment section and we will be happy to answer you.
If you want to encourage our efforts, please do like this video, and for more videos, please do subscribe to our channel. Thank you once again.
Thank you.